Okay, today I want to talk to you about Hess's law. This is a thermochemical equation. Just like other equations, this has a reactant and the product side. What is so different about this equation is that the change in enthalpy is given to you. All thermochemical equations indicate the direction of the energy flow in relation to the system. Since a negative sign is given, the energy of the system is moving out of the system, indicating this as an exothermic reaction. All thermochemical equations can be broken down into intermediate steps with a particular change in enthalpy for that step. If all the intermediate steps and change in enthalpy for each intermediate step is added together, then the overall change in enthalpy can be determined. If you look at this equation, reactant A is eventually yields product D. There is an overall change in enthalpy for this entire reaction. However, intermediate steps do exist to make reactant A product D. Step 1, in order to convert reactant A to B, there is a change in enthalpy 1. Step 2, B gets converted to C, and that is a change in enthalpy 2. In step 3, C is converted to product D, that is a change in enthalpy 3. This is the basis of Hess's law. Hess's law states that the overall change in enthalpy 4 and change in enthalpy 1 and change in enthalpy 2 and change in enthalpy 3 are the exact same. That is to say that if the change in enthalpy of a step is not known, then that missing change in enthalpy can be easily determined. So if the individual change in enthalpy is known for each step, then the overall change in enthalpy can be determined. Through this process, the overall change in enthalpy is not a surprise because you can see at each step whether the reaction is going to become an endothermic or an exothermic reaction. It is the exothermic reactions that are the most concerning because the exothermic reactions release energy, which means that the reaction goes boom. This knowledge prevents any unexpected explosions. This is why Hess's law is so important. It helps to predict the type and the amount of change in enthalpy in a chemical reaction. So if we look at this right here, you have a diagram that is illustrating the same information. That is illustrating the exact same information. So you have here the reactant that has an overall change in enthalpy to produce the product. However, if we do not know the change in enthalpy for this reactant that eventually produces this product, then we can use the intermediate steps to determine the overall change in enthalpy. So you would start off with the reactants that are given to you, and the first intermediate step would become your product. There is a change in enthalpy that you have for that step. Step 2, now the product of step 1 will become the reactant of step 2, and you will now have a new product in place with its own particular change in enthalpy. Step 3, the product of the previous step now becomes the reactant of your step, and you now have your final product that is written, and there is a change in enthalpy for that step. You can now take all of these enthalpies and add it up. Notice that because you have several intermediate steps, a lot of these compounds should cancel out. The rule for canceling compounds is that you can only cancel compounds that are on the opposite side of the arrow, and you have to look at the total number of moles for the compound. So, let me see. If you look at this equation right here, if you look at this equation, you've got aluminum oxide that is in the product, and you have aluminum oxide that is in the product, that is in the reactant. Both of these can cancel out. You have 2 moles of liquid iron in the product, and you have 2 moles of liquid iron in the reactant. These two can cancel out. You have aluminum oxide, again, solid, that's in the product, and aluminum oxide in the third step in the reactant that can cancel out. Now you have 2 moles of iron solid that can cancel out with 2 moles of iron solid here. So the remaining compounds is your final equation, and this final equation should be the same equation as what you were given in the original equation. As far as the enthalpy goes, since we are adding up everything together, you are again going to add up the enthalpies also, keeping in mind the signs. You're going to add it up, and this change in enthalpy is a negative 851.1 kilojoules. That means that energy is flowing out of the system. Whenever you are adding up using Hess's law, keep these in mind. Keep these in mind that in order to cancel the compounds, they must be on opposite sides of the arrow, and that the total number of moles must be the exact same. Let's do another practice. So you've got this equation. Okay. So here are the rules for solving Hess's law. If a reaction is reversed, then the sign change in H also changes. And number 2, if you multiply the reaction by a factor, its change in H is multiplied by the same factor. So here's an example. We have an equation, 2 moles of solid carbon plus hydrogen gas produces acetylene gas, and we don't know what the change in enthalpy is at the moment. However, we do know the intermediate steps, or the individual steps that you don't see in the original equation that are still present. So you have acetylene here, acetylene gas, in the reactants for step 1 of the intermediate. However, notice on the original step here, and I'll move it up. So you have acetylene in the reactant in step 1, but notice that acetylene is in the product of your original equation. So it would definitely help to flip this equation around, to flip it so that the acetylene can now go into the product side, just like your original equation. What you can do is you can multiply this by a negative sign. This negative sign indicates that you're flipping the equation, and you're changing the sign right here for the change in enthalpy. So since you're flipping it, the negative will now become a positive change in enthalpy. You're going to multiply by 1 because this is 1 mole of acetylene, and this is also 1 mole of acetylene. So multiplying it by 1 will not affect the mole of anything in this equation. So your new equation is 2 moles of carbon dioxide gas plus 1 mole of liquid water produces 1 mole of acetylene gas plus 5.5 moles of oxygen gas. And your change in enthalpy is now a positive 1,299.5 kilojoules. Notice keep in mind once again that the signs have changed. The next one you were looking at, the oxygen and the carbon dioxide, we do not need to worry about in step 2 because they are not present in the original reaction. However, the compound from step 2 that is present in the original reaction is the solid carbon. So you're looking at the solid carbon in the original reaction. In the original reaction, you have 2 moles of solid carbon. Over here, you have 1 mole of solid carbon. So you need to double this or multiply it by 2. So you can take step 2 and you can multiply it by 2. That means you're going to double it. When you double this reaction, that means you're going to multiply by 2. So you have 2 moles of carbon solid, 2 moles of oxygen gas. That produces 2 moles of carbon dioxide. Since you were multiplying everything by 2, you're also going to multiply the change in enthalpy by 2. But this is not where you multiply a negative times a negative becomes a positive. Don't do that. Instead, you're going to simply multiply the number by 2, but keep the sign as it is. So the negative sign will remain, and you're going to multiply 393.5 by 2, and that should give you 787 kilojoules. The third step is, once again, you were not worried about the oxygen or the water because your original equation does not have that. The compound that you are looking at is the hydrogen gas because the hydrogen gas is in the reactant side as well as in the original equation. It is in the reactant side. This is 1 mole of hydrogen gas, and this is also 1 mole of hydrogen gas. So there really isn't anything we need to do to this equation. The number of moles is the exact same, and the compounds are in the exact same side of the arrow, which is the reactant side. So we're going to keep this as it is. There is no change, and it stays the same. So we're going to keep everything in this equation the exact same. So we're going to have in this equation hydrogen gas, 1 mole of hydrogen gas, half a mole of oxygen gas, which produces 1 mole of liquid water. The change in enthalpy, we're going to keep the exact same, so that's going to be negative 285.8 kilojoules. Now we're going to go back and we're going to use Hess's law, and we're going to add all this up to get our overall change in enthalpy. So we're going to go back and we're going to start canceling out all the compounds that have shown up in the intermediate step but are not present in our original equation. So you're going to go back and you have 2 moles of carbon dioxide in the reactant side. In order to cancel it, we've got to have 2 moles of carbon dioxide, but in any other step other than step 1, we've got to find it in the product side. And there's 2 moles of carbon dioxide. So we can cancel the carbon dioxide. The next one is water. We have 1 mole of liquid water, but 1 mole of liquid water does not exist in step 2, but we do find it in step 3. So it's 1 mole liquid water in the product side, so we can cancel that. The last one we are going to look at is oxygen in here. Now this is 5/2 moles of oxygen gas. If that number happens to confuse you, then you can always put 2.5 moles. You can put the decimal there. So in step 2, you've got oxygen here, oxygen gas, but 2 moles of oxygen gas. And then in step 3, you have half a mole of oxygen gas. Together, this is 2.5 moles of oxygen gas. In the reactant side, that cancels out the 2.5 moles of oxygen gas in the product side of step 1. So with all the intermediate steps and the compounds canceled, you have your original equation. You should actually have your original equation, and now we can go back and we can add up the change in enthalpy. So if we add up the change in enthalpy in this case, when we keep in mind the plus and minus signs, and the overall change in enthalpy should be 226.7 kilojoules. In this case, this is an endothermic reaction. So let's look at the second example. And in the second example, you have here carbon disulfide, 1 mole of carbon disulfide, and you have 3 moles of oxygen gas that produces 1 mole of carbon dioxide plus 2 moles of sulfur dioxide gas. Now, we're going to go ahead and calculate Hess's law for this. So we're going to look at the intermediate steps. In this case, just like the other equations, we are given the change in enthalpy for each of the intermediate steps, but we do not have the change in enthalpy, the overall change in enthalpy for the original reaction. So we're going to start off. In this case, we've got 1 mole of carbon, but 1 mole of carbon does not exist in our original equation. We do have oxygen, and then we do have carbon dioxide also in our original equation. So we're going to look at 1 mole of carbon dioxide that's in the product side, and then we also have 1 mole of carbon dioxide that's in the product side of our original equation. Since the number of moles is the exact same, and since the compound is present in the product side, both in the original and in step 1 of the intermediate reaction, we are not going to make any changes to this reaction. So we're going to say no change, it's going to stay the same. Looking at step 2 of this equation, we've got sulfur that is not part of the equation. We've got oxygen again, but then we have in our product side sulfur dioxide that is present in the product side. We have 1 mole of sulfur dioxide in the product side of step 2, but in the original equation, we have 2 moles of sulfur dioxide present in the product side of our equation. So even though it's in the product side, the number of moles do not match up. So we're going to multiply this whole step 2 by, we're going to double it or multiply it by the number 2. And when we do, we've got 2 moles of sulfur dioxide plus 2 moles of oxygen. Let me go back. 1 mole, we've got 2 moles of sulfur solid plus 2 moles of oxygen gas that produces 2 moles of sulfur dioxide gas. Now, since we are multiplying by 2, we are going to just double the number value only. So 296.8 kilojoules per mole, you're going to multiply by 2, and that should give you 593.6 kilojoules per mole. And don't forget that, once again, this is not where you multiply negative times negative. Rather, you're going to carry this negative sign down with you. In the step 1, we had 1 mole of carbon solid plus 1 mole of oxygen gas that produces 1 mole of carbon dioxide gas. And since we didn't do anything, we are going to keep the change in enthalpy the exact same. So that is negative 393.5 kilojoules per mole. The last step that we have here is 1 mole of solid carbon plus 2 moles of solid sulfur that produces 1 mole of liquid carbon disulfide with a change in enthalpy in the positive 87.9 kilojoules per mole. Notice that both carbon and sulfur are not present in the original equation, so we're not going to worry about it too much. But we are looking at the compound that we are going to focus on is this 1 mole of carbon disulfide that is in the product side of step 3 of our intermediate equation. If you look at the original equation, 1 mole of carbon disulfide is present in the reactant side. Since carbon disulfide is on opposite sides of the arrow, in the reactant side in the original equation and the product side of our step 3 of our intermediate equation, the location is the exact same, and the number of moles, the location is not the same. They're on opposite sides of the equation. But we need to get the carbon disulfide on the same side of the equation. So we're going to flip it over, which means that we're going to multiply by negative side. Since the number of moles is the same and we don't need to change the number of moles, we're just going to multiply by 1. So we're actually going to multiply by -1 to flip this equation around. And when we flip the equation around, you're also changing the sign on the change in enthalpy. So in this case, our third intermediate step will be 1 mole of carbon disulfide liquid present in our reactant side that will produce 1 mole of solid carbon plus 2 moles of solid sulfur. And our change in enthalpy, it will now become a negative 87.9 kilojoules per mole. So now that we have our equation written for Hess's law, we can just add everything up. We need to first cancel any compounds that are repeating. And so keep in mind that in order to cancel a compound, it must show up in a different step on the opposite side of the arrow. And the number of moles must add up. So if you have 1 mole of solid carbon in the reactant side of step 1, we've got in step 3, we've got 1 mole of solid carbon in the product side. So we can actually cancel the reactant in the product. We've got 2 moles of solid sulfur in step 2, that's in the reactant side, and we've got 2 moles of solid sulfur in the product side of step 3, so we can actually cancel it because they're on opposite sides of the arrow, and the number of moles actually cancels out also. So the compounds that are remaining should be part of our original equation that we have, and they should be the exact same. So we should have 1 mole of liquid carbon disulfide plus 3 moles of oxygen gas. That produces 1 mole of carbon dioxide gas plus 2 moles of sulfur dioxide gas. In our change in enthalpy, in this case we are going to start adding up our change in enthalpy, but we're going to keep the signs as they are originally. So when we start adding it up, our change in enthalpy for our overall reaction is negative 1075 kilojoules per mole. Notice that this is a negative sign, which means that energy is leaving the system. It's an exothermic reaction, so an explosion is going to happen. We can actually predict that the end of this equation of all these intermediate steps, that this equation that we have is going to be an explosion, because as you are going through each of the enthalpies for each of the steps, intermediate steps, you can see that the negative sign is that there is a prominent negative sign that is developing, or that a prominent exothermic reaction is occurring. So the change in enthalpy, you can see it from the very beginning, that the change in enthalpy is becoming more exothermic. In the example above that I did, you can actually see that with step 1, you can see that the change in enthalpy is a very large positive number. And then the other 2 enthalpies just don't add up. So this is going to be an endothermic reaction. you can predict it as you go through each of the steps, the type of reaction that's going to be. It's Hess's law that helps us predict the type of reaction and makes it easier for us to predict whether an explosion is going to occur or not occur. Hess's law is helps us predict any of those unpredictable explosions, which is what we don't want. So that is the purpose of Hess's law.